car, and this is a Formula One car. Both vehicles are open-air, open-wheel race cars that can reach over 200 miles per hour on their tracks. IndyCar is relegated to only North America, while Formula One racing is practiced all over Europe. Both cars have significant differences and have never raced each other before. So I want to answer the question, what if we raced both Indy cars and Formula One cars on the same track? Now, to answer this question, let's look at the specs of each car. The Indy car has the power of 700 horsepower, while the F1 car has 760 horsepower. This is because the Formula One car has significant advantages in development. F1 cars cost a lot more than Indy cars and have a lot more technology put into them. Now let's compare top speeds. The Indy car has a top speed of 370 kilometers per hour, or about 103 meters per second, while the F1 car has a top speed of only 320 kilometers per hour, which is roughly 88 meters per second. The Indy car has less horsepower, but can travel at a higher speed. Now, this will be answered later on, so let's move on to acceleration of both cars. Different tests concluded by Formula One and IndyCar's websites have said that these cars can go from 0 to 160 kilometers per hour in different amounts of time. The Indy car, 2.9 seconds, and the Formula One car, 2.2 seconds. Now, this makes sense because it has more power, it should accelerate faster. So let's calculate acceleration. Calculate average acceleration. I'm going to divide the change in velocity by the change in time. So the change in velocity for both cars is 160 kilometers per hour, which I converted to meters per second, so it would make more sense. The acceleration for an Indy car is about 9.58 meters per second squared, while acceleration for an F1 car is about 12.63 meters per second squared. Which makes sense. If it has more power, it should accelerate at a higher rate and have a lower time to accelerate. Now let's see how long it takes both cars to reach their top speeds. To use that, I'm going to use the formula VF is equal to VI plus AT. VF for the Indy car is going to be 103 meters per second. Acceleration is 9.58 meters per second squared times t. And t for this case is about 10.75 seconds. I'm going to do the same for the F1 car. It has a top speed of 88 meters per second and accelerates at 12.63 meters per second times t. So in this case, t is going to equal 6.97 seconds. Now this is the time it takes for both cars starting from rest to reach their top speeds. F1 car can reach its top speed in roughly 7 seconds, while it takes almost 11 seconds for the Indy car to reach its top speed. Next, let's see how these cars would react in a drag race. Now to do this, both cars are going to start on a straight section of track and accelerate using that same average acceleration. Now I want to calculate what is the time it will take for both cars to reach the same position. So I'm going to use the formula delta D is equal to VIT plus 1/2 AT squared. Now delta D is going to be equal for both cars because when they're at the same position, they'll be neck and neck with each other. However, both cars accelerate for a period of time and then switch to a constant velocity. So for the Indy car, it's going to accelerate at 9.58 meters per second for 10.75 seconds. And after the 10.75 seconds, it will be traveling at 103 meters per second for a constant period of time. Now for the F1 car, it's going to be accelerating at 12.63 meters per second squared for 6.97 seconds. And then it'll travel at 88 meters per second for time t, but t plus the additional time that the F1 car plus the additional time was traveling its top speed. So that's found by taking 10.75, the time it takes for the Indy car to reach its top speed, minus 6.97, the time it takes for the for the F1 car to reach its top speed. Now we solve for t, and we get t is equal to 5.633 seconds. Now this is the time after the Indy car reaches its top speed when both cars are traveling at the same velocity. So if we start at time 0, that time will occur 16.38 seconds after both cars start. And the distance that is covered is roughly 1,134 meters. So if both cars start on a straight section of track that is over 1 kilometer in length, both will be even by 1 kilometer. And anything longer, the Indy car will be in first place. So if we look at a track like the famous Indianapolis 500, if both cars were to start at this section right here, because this section is over 1 kilometer, and accelerate, the Indy car would be in the lead. Now let's look at the weight of both cars, because we want to talk about cornering next. So weight is equal to mg. So for an Indy car, we know its mass was about 715 kilograms, so its total weight will be about 7,000 newtons, while an F1 car weighs about 6,300 newtons. However, this is not the total weight of both cars. Both cars implement things called downforce in order to have stability on the track. So downforce uses Bernoulli's principle to push the car down when it's traveling at high speeds, because both cars have mass and weight when they're driving and when they're stationary. So this is just mg. However, the downforce exerts an additional force that's usually much larger than the weight of the car. Now this is through the front and rear wings of the car. This is the rear wing, this is the front wing that push the car down when it's traveling. So at high speeds the car can be quite stable. And this has an adverse effect on the top speed of the car. So let's take that into consideration. Using data from Formula One's and IndyCar's websites, I know that the Indy car has roughly 21,000 newtons of downforce pushing it down when it's traveling at 200 miles per hour. But the F1 car has 24,000 newtons when it's traveling at 200 miles per hour. So the total weight of both cars when they're traveling at 200 miles per hour is 28,000 newtons for an F1 car, for an Indy car, and 30,300 newtons for an F1 car. So we see that even though the Indy car has more mass, it weighs a lot less than the F1 car because it has a lot less downforce. So this is why it has a higher top speed, even though it has less acceleration and less power than the F1 car. So now that we've looked at weight, let's consider the cornering ability of both cars. So in order to solve for cornering ability, I use the formula mv squared divided by r is equal to force of kinetic friction. Now, let's consider a very famous track, the Indianapolis 500. Now, right here we see that our turns have a very large radius. Radius, according to Indianapolis 500's website, is about 180 meters. And if we examine closely, we see that the corners are banked. And this angle right here is about 9.2 degrees. Now, when we consider banked turns, we have to look at the components of the car's mass and the normal force. Since its mass goes straight down, we just draw an arrow going straight down. However, normal force is up at an angle. So we can see that we have some component of normal force acting in the same direction as friction. Now this helps bring the car down instead of sliding up into the curve, so we have to consider the mass of the car when we're solving, the mass of the car that's sliding itself down when we're solving for this problem. So to solve for banked turns, such as the Indianapolis 500, we're going to have to modify our formula. Our formula becomes mv squared divided by r is equal to u mg plus force of downforce times cosine theta plus mg sine theta, because this is the force of the car's actual mass pulling itself down the hill. So on the Indianapolis 500, the radius is 180 meters, and the bank angle is about 9.2 degrees. And for both cars, which use racing slicks, according to Firestone's website, have a coefficient of friction of about 1.50. Now, if we plug in these values and solve for V, we see that an Indy car can negotiate that turn at roughly 103.5 meters per second, while an F1 car can do it in about 110.3 meters per second. Now this is very close to the top speed of an Indy car, so the driver will only have to back off a tiny bit in order to take the turn without flying off the track. But an F1 car, this top speed of the turn is much higher than the actual car's top speed, so the F1 car can take the turn at full throttle. However, full throttle is only 88 meters per second, while full throttle for an Indy car is 103. So we see on the Indianapolis 500 track, if both cars were to start here at the longest straightaway and accelerate, the Indy car would take the lead and continue having the lead throughout all corners. So if a track has very long straightaways and very wide corners, we'll see that the Indy car has the advantage due to its greater top speed. Now let's consider a different track, something with less straightaways and more turners. Let's look at Monaco. So Monaco Grand Prix is one of the most difficult courses in Formula One racing. This is because we have a lot of very sharp turns and very thin passageways. Here you have to really take your time making a turn, or else you'll end up in the corner. So on the Monaco Grand Prix, radius is only about 60 meters in some of the tighter turns, and these corners aren't banked, so theta is equal to 0. So we can rewrite our formula to be mv squared divided by r is equal to mu mg plus force of downforce. Now we solve for v squared for both cars, and we see that an Indy car can negotiate one corner at 59.4 meters per second, while a Formula One car can negotiate the same corner at 65.3 meters per second. Now, since both these speeds are under the top speed of the car, we'll see that they have to slow down in order to take the corner. However, the F1 car doesn't have to slow down that much, because it can take the corner at a lot faster speed than the Indy car. So on tracks like Monaco, we see that the F1 car will have an advantage because it doesn't have to slow down as much and can go through corners a lot quicker than the F1 car. So if both cars were to start at this longest section right here, the Indy car may pull ahead because of its higher top speed on the straightaway, but it would have to slow down a lot more on the turns and allow the F1 car to pass. So on tracks like this, the F1 car would have an advantage. Now let's consider a track where both cars would be equal. We see it would have to be made up of long straightaways and wide turns, but also some very tight corners to give the F1 car an advantage. The most perfect example for this is the Shanghai Grand Prix circuit. Now this circuit has two very long straightaways. These are some of the longest straightaways in Formula One history. They're both over 1.6 kilometers each. And here we'll see that the Indy car will have a great advantage due to its very high top speed. However, a big section of the track is also a lot of sharp turns and bends. Here, the F1 car would have an advantage because it can negotiate these turns much quicker and accelerate out of them much faster. So on this track, I predict that both cars would be about equal. So if both Indy cars and Formula One cars were to race each other, the outcome of the race would depend on the track layout. Track layouts that favor a lot of shallow corners with banked turns and long straightaways would definitely favor the Indy car because of its higher top speed. However, if a track has unbanked turns that are very sharp, the F1 car is favored due to its increased cornering ability. And finally, tracks that are made up of a combination of long straightaways and sharp turns would favor both cars equally, so both cars would be tied when they finished.